Our lecture for this week will be about Monte Carlo methods and Monte Carlo simulation. Let's talk about the principles of Monte Carlo methods. We will look in a little bit more detail at Monte Carlo integration and also at Monte Carlo simulation applied to statistical tests for looking at their coverage and their power. But Monte Carlo methods in general are a very frequently used way of simulating and using random sampling for estimating various types of problems, such as optimization, numerical integration, but also sampling from complex probability distributions. Later in this course, we will look at Markov chain Monte Carlo simulation, which is the more applied version of this and more advanced version of this. And also we will look at determining coverage rates of confidence regions and acceptance regions of tests. So what is the principal notion of Monte Carlo methods? Originally, these simulations were tested as previously understood deterministic problem and applied statistical sampling to estimate uncertainties in the simulations. So we had confidence bands for models, we have confidence bands for actual measurements. On the other hand, we have Monte Carlo simulation, which is doing quite the opposite of this approach. We try to solve the deterministic problem by applying probabilistic simulations. So what's the history of this? In the 1940s, mathematician Stanislav Ulam, who was working on the Manhattan Project and quite famous for that later on, fell sick and had to stay on sick leave for several weeks. And to pass his time, he started playing solitaire. And at some point, he asked himself, well, how often do I set this up and actually lose? This was well in the times before we had the ways of playing solitaire on the mobile phone without having to do this tedious reshuffling on our own. So this was really about how much time do I lose with just setting this up and still losing the game. And he wanted to calculate his probability. Being a mathematician, he thought that he would be able to figure out all these combinatorics, but at some point he just stopped. It was too difficult to do it analytically, and he decided there must be another way of doing this. And he tried to do it in the way of doing physical simulation by playing games and recording how often he lost or how often he won, and try to estimate the probability based on this. Since this was the time before having computers doing the reshuffling within split seconds, this also turned out to be infeasible. So at some point he decided to use computational power from an actual computer, and he turned to his friend John von Neumann, very famous informatics person, one of the leaders in this field back in the 1940s. And both of them worked together on the Manhattan Project, and they discussed this idea how to simulate the solitaire probabilities on the most expensive computer of that time. And they did it. The calculations used up several hours of computing time in the times when these were costing tens of thousands of dollars, but still they did it. And this bore the idea, which they also later on utilized for the actual Manhattan Project and other projects other famous names in this field, such as Nicholas Metropolis, who is famous for Metropolis Hastings sampling, this kind of special version of Markov chain Monte Carlo sampling. So this gives a very good idea what is the backbone of Monte Carlo simulation. We want to simulate physical processes in order to estimate underlying properties, underlying probabilities based on those. So to do this, we have to define the actual domain for our possible inputs of the problem. And only once we know which domain we want to simulate on, we can specify a probability distribution over this domain, and then perform deterministic computation on these inputs and aggregate the results. It's always the same steps. So let's see how Monte Carlo simulation works out for trying to estimate the value of pi. We have here 100 random numbers in the square, the unit square, and we look at the proportion of random numbers outside of the quarter of the circle within this unit square, and we see the first approximation is 3.16. Using another 200 points, we now get an approximation which is quite worse, 3.066. Using another 1,000 points, we get a new approximation, 3.19. Compared to the previous one, this is an improvement. And with almost 3,000 points, we then get an even better approximation, 3.167. And we can imagine that we could continue this, fill up this unit square with the actual points, see the squared part of the circle within the unit square, and try to estimate this ratio and therefore estimate pi. So this gives us the motivation of what we actually want to do. We want to generate random points, random values, random variables x from a given density f of x. And we assume that we will use another function, an arbitrary function h, to transform these points. And our actual problem of interest is to integrate this function h of x with respect to x within a given interval a to b. So classically, if these x values would not be randomly distributed, this would amount to calculating the area under the curve h of x within the interval a to b. However, we have random variables now. So in this scenario of randomly distributed variables x, this transformation is actually calculating the expected value under the density f of h of x. So basically, Monte Carlo integration wants to approximate this expected value of h of x, and it does so by calculating the approximation of the expected value, which is the arithmetic mean. And therefore we take the arithmetic mean of all our simulated values xi, transform by the function h, sum them up and divide by the total number of simulated values. According to the strong law of large numbers, this arithmetic mean converges almost surely to the expected value of h of x. So this leads us to the large sample theory behind this. The central limit theorem holds here, and therefore our arithmetic mean of the H transformed values minus the actual expected value we want to simulate divided by our sample variance is normally distributed, standard normally distributed. And therefore, we can also, based on this, construct convergence tests and confidence bounds for our expected value. So this is the theory behind all this. Since we can construct these confidence bounds, we also measure our confidence with the mean squared error, typically to evaluate how well our simulation is performing. So the mean squared error basically is the expected value of our quadratic deviance from an actual estimate. And also this mean squared error is simulated in the very same way. We take our actual simulated values, subtract them from what we wish to learn, square these deviances, and take the arithmetic mean of those. So for, as a quick example, we have standard normally distributed values. We simulate therefore from the standard normal distribution, and we take the median of all those and wish to learn how well the median is performing as an estimator within 1,000 samples. And therefore we take the mean of the quadratic deviances of the median from the true underlying expected value, and we get a mean squared error of 0.046. So this is the first step of applying this Monte Carlo simulation to get an idea of how well the median itself as an estimator of location is performing in this scenario. Now let's take a look at the Monte Carlo integration part. So we really use Monte Carlo simulation to do the actual calculation of an integral of the area under the curve. In this case, the curve is x to the power of 4, and we wish to integrate it between 0 and 1. And in order to do so, we simulate x values from a uniform distribution between 0 and 1. The Monte Carlo integral for 100,000 simulations leads to a value of 0.19917. The numerical integral based on Newton-Raphson not Newton-Raphson, based on numerical integration methods which are doing geometric approximation of this area under the curve. They calculate 0.2 as the actual value for this integral, and the exact integral, which we can easily calculate in this case, is exactly this 0.2. Another example, another interval. We look at the sine of x. We look at the integration of this sine function between 2 and 5. Here now we do not have the standard interval just between 0 and 1. Therefore, we can see for the first time now how the distribution of the values x is coming into this Monte Carlo integration here. We have here the f of x density function of the uniform distribution within the interval 2 to 5, and we have the function sine of x, of course, which we wanted to integrate. And therefore, in order to end up with the actual integral, we multiply by the inverse of this 5 minus 2. This leads us to a value for this integration, which is the mean of the sine function of our simulated values times the 5 minus 2. This is similar to what numerical integration by geometric approximation will lead us to, and also similar to what the exact integral would be, which is the cosine in this case. So let's take another step a little bit further. We can also do this, of course, by not just integrating with respect to a single variable, but also with respect to several variables, integrating one after the other, taking one mean after the other, and looking at the results for those. So we look at simulated values for the x's and for the y's, in this case the u's and the v's, and for both at the same time we take this arithmetic mean and therefore end up with the Monte Carlo integral within the three-dimensional space. What happens if we do not use the uniform density as our density for generating these values x? We try to approximate the integral e to the power of minus x squared, integrated over 1 to infinity. As we should be aware, this is something which does not have an analytical solution, so therefore in this case we do not have the analytical solution as a comparison. We only have numerical integration here as an option to do this, and a reasonable way of approaching this would be to say, well, e to the power of minus x squared, this is something which is related to an exponential distribution in a way. So if I were transforming this integral to an e to the power of minus x plus 1 squared, I would get a part in here which is similar by its definition to the exponential distribution. If you remember last time we were looking at all these different distributions, we will use them in almost each and every one of our lectures in the course now. So there's this connection in here. Take a look at those density functions to see how this relation is really working. But what we are doing here is we take this transformed integral and then we again have to divide by the actual density of the exponential function from which we were simulating. As before, we divide by the density values in order to end up with something which is on the actual scale where we want to be, and therefore we end up with the Monte Carlo integral pretty close to what the geometrically based numerical integral would tell us in this case. So we see that Monte Carlo integration is working. What about convergence and variance of the thing? Let's take a look at how this is performing. The variance, of course, is the actual value which we want to estimate, the expected value of the h of x, minus the values we simulated, the h of x values, and we take the squared deviance of that and have to reweight it with our density function f, which is basically the variance of this h of m. And again, we simulate it in the Monte Carlo way. We take our simulated values x, plug them into our function, subtract the arithmetic mean as the approximation for the expectation, take the squared deviances and divide by the m squared. This gives us an estimator for variance and also for the standard deviation of the Monte Carlo estimator of this arithmetic mean estimator. There's a specific subpart of Monte Carlo simulation which is named important sampling. Important sampling basically focuses on the values where we have the highest chance of them being useful for calculating the integral. What I mean by being useful, let's take a look at one of these curves. So within the sampling area, we have parts where there's more relevance for sampling and parts where there's less relevance for sampling. And importance sampling basically focuses on simulating values from the parts where we need them, where we need more values to estimate the integral well, and putting less importance on the parts where we do not need so many of our values. And this importance weighting is what specifically goes into this important sampling algorithm to change a little bit how for this Monte Carlo simulation technique, which it actually is, the values are simulated and then also reweighted again to see we want to focus on specific areas. So yeah, this is Monte Carlo integration. It's really about integrating this h of x function and approximating it basically by nothing else but an arithmetic mean, which is a completely different idea from using any kind of geometric shapes to approximate areas under the curve, but it's still working pretty well, as you have just seen. So let's use this Monte Carlo method for something completely different. We want to look at hypothesis tests and the construction of confidence intervals. So we've seen before that we can easily obtain these mean squared errors and percentiles, but we want to evaluate also the coverage probabilities of confidence intervals. We want to evaluate the power of tests and compare performance of different methods based on this Monte Carlo simulation. In order for this, we revise a little bit what hypothesis testing actually was about. Remember, there are two hypotheses going into this, a null hypothesis and an alternative hypothesis, and those two are not exchangeable. They are not balanced in any way. The null hypothesis is creating our basic scenario under which we are running our tests. The alternative hypothesis is what we are actually interested in. We can only reject the null hypothesis. We can never prove it in any way. Related to this is also the idea of significance and confidence. Significance level alpha, which is specified, is basically the probability to reject the null hypothesis incorrectly, whereas confidence is 1 minus this alpha level. It's the reliability of being close enough in the area where we are close enough to the null hypothesis scenario to not fall into the significant area of rejecting the null hypothesis. The p-value, the most important and wrongly interpreted value ever in statistics. The probability of actually observing a sample estimate or a more extreme value given the null hypothesis were true, which is the probability of falsely rejecting the null hypothesis for a given data. So how is this related to confidence interval coverage? basically we would specify the confidence level. Once we specified the significance level, the confidence level is automatically 1 minus this alpha. However, unfortunately, life isn't as perfect as we would like it to be in mathematics, and therefore for actual data plugged into these confidence intervals, it's not always 1 minus alpha times 100%, which is the real coverage of the confidence intervals. It might be something less or something different. And therefore, we try to estimate how different this actually is and take a look at 1,000 simulations. We want a value alpha specified as 5%, and we look at the chi-squared interval with n minus 1, 30 minus 1 degrees of freedom. 30 is always the rule of thumb for where things are still performing nicely. If it's above 30, it's not, it's well enough, it's working well enough. If it's less than 30, it's not. So we took just this usual boundary, which is a rule of thumb in statistics. And we end up with this corresponding quantile. What we want to replicate is what's happening when we actually plug this into the construction of confidence bounds. And here we have the lower and the upper confidence interval boundary. And we end up with these confidence intervals for different types of simulation. And we see the coverage, although we wanted to have 95%, is 95.6%. So we're off from the 5% significance which we would have liked to have. Not so nice and not exactly what we wanted. And apparently not everyone is aware of it. So you're now aware of the fact that even if you construct a 95% confidence interval, it might not cover 95%, but something else. So let's take a look at statistical errors once we are revising hypothesis testing in general. We remember that if the null hypothesis were true or if the null hypothesis were false, we will always do nicely and correctly if we keep with a true null hypothesis, and if we reject a false null hypothesis, then we're doing the right decision. However, if we reject a null hypothesis which were actually true, we are performing this type 1 error. The false positive rate, which is the significance level alpha, is exactly the amount of this type 1 error. On the other hand, it can happen that the null hypothesis is false. However, we do not recognize that this is the case, and we still keep with the null hypothesis. This is the false negative which is happening, and therefore estimated by the false negative rate beta, the probability of a type 2 error. 1 minus this false negative rate beta is named the power, the probability of correctly rejecting the null hypothesis. And again, this power is something which is unlike the confidence level alpha, which we are specifying at the beginning of any testing scenario, something we have to calculate to approximate because we do not know what this value is exactly. So remember that this power is related to the sample size. The more samples we have, the more power we have. It's related to the significance level. The smaller the significance level, the smaller the power, which is bad. Smaller significance level means smaller type 1 error, but unfortunately it also means a larger type 2 error. So we cannot make it as small as we want. And then there's the effect size, what we actually want to be able to measure, how exact we can become. And this effect size, the larger the effect is, which we want to detect, the larger the power, the smaller the effect, the smaller the power. So this leads us to the idea that we actually would like to know what is the true probability of correctly rejecting this null hypothesis for any order of magnitude, for any effect size of this delta. So with a given effect size, we wish to know how close we can get. And as you can see, the power level is again increasing once we increase the size of the effect. And this is happening down here. We're replicating for the t-test scenario with random normal input variables, how large this power, this correctly rejecting the null hypothesis is, and end up with something like this. For our largest effect, we also have the largest power. For those, for small effects, 0, we also have a very small power of actually getting this correct. Good. This is basically the end of our course for today. You have all your lecture material online. You also find the slides online, and you will also find your exercises, which ask you to try out a little bit how to use this Monte Carlo integration for different scenarios and work with those. And I wish you good luck with all your exercises and all the best.